So I wanted to wrap up our discussion of sampling distributions by talking about sampling distributions for counts and proportions. Often something that we're interested in knowing about the population is not the average of something in the population, but rather the proportion of something in the population. For example, what proportion of all voters are going to vote for Trump? Now, some books talk about this in terms of counts, like how many people in the population will vote for Trump, but most books treat this as proportions. So we have a proportion for the population, which is referred to as P, and we have a proportion for our sample, which is referred to as P hat, which can be calculated by X over N, the number of successes, quote unquote, in our sample divided by the sample size. So, similar to how we progressed with the sampling distribution of X bar, we're going to talk about the same topics with the sampling distribution of P hat. The center of the distribution of P hats. The mean of the P hats is the population P. If you sampled over and over again and created a sample proportion, P hat, for every sample, and kept a list of all of those P hats, the average of all those P hats should be the population P. This will always be true as long as you have a simple random sample. So, redoing an example similar to what we did for means. Suppose I have these same three numbers, 1, 2, and 6, but what I'm interested in is what proportion of the population is prime. So only the number 2 is prime, so the proportion of our population that's prime is 1/3. And now let's look at what happens when we take samples of size 2 and we see what proportion of our sample is prime. So once again, these are all the samples of size 2 that we could get if we're sampling with replacement. And now we're going to calculate the sample proportion for each of those samples. In this first sample, with the number 1 and the number 1, none of the sample is prime, so the P hat for that sample is 0. In this sample here, with a 1 and a 2, half of the sample is prime, so we have a P hat of 0.5, and so on. So I figure out all 9 of those P hats. And then if you take the average of all those P hats, that means adding all those P hats together, dividing by 9, which comes out to be 3 over 9, which is 1/3, which is exactly what the population P is. So the mean of the P hats is the population proportion P. And notice the mean of the P hats is the population P, 1/3, even though none of my individual P hats were 1/3, but the average of the P hats is 1/3. Next, we talk about the spread of the distribution of P hats, or the standard deviation of the P hats. And that is this formula here, radical P times 1 minus P over N. This is somewhat related to the standard deviation that we learned for binomial, which is radical N times P times 1 minus P. The number in our sample that have a certain characteristic can be considered a number of successes, and the proportion in our sample that have that characteristic is the number of successes divided by the sample size. So if I want to do the standard deviation of the P hats, I can do the standard deviation of the successes divided by N. And the standard deviation of the successes is radical N times P times 1 minus P. And if you divide that by N, you get radical P times 1 minus P over N. So once again, we have radical N in the denominator. So as the sample size increases, the distribution of the P hats becomes less spread out. The spread of the distribution of P hat decreases, meaning that all of the P hats will be closer to the population P. So just to check this with our earlier example, according to our formula, the standard deviation of the p-hats should be radical p times 1 minus p over n, so that should just turn out to be 1/3. But we already have listed all of our p-hats, so we can figure out the standard deviation of the p-hats like this. Each of the p-hats squared minus the sum of the p-hats squared divided by n, and that also comes out to be 1/3. So just a real quick kind of verification that that formula for the standard deviation of the p-hats works. And a similar alteration that's sometimes used that we saw with the standard deviation of x bar, if you're not sampling with replacement, then sometimes this more difficult formula has to be used with this extra radical tacked on at the end, exact same radical adjustment called the finite population correction, same thing that we saw in the video on the standard deviation of the x bars. Then let's talk about the shape. There are certain conditions under which the distribution of p-hat looks approximately normal. But it's not based on sample size alone, like that magic number of 30 that we had for the sampling distribution of x bar. It's actually related to a rule of thumb for when the probability distribution of binomial looks approximately normal. So if we can look at this over here, here's a little app to illustrate this. So if we have a binomial random variable with just one trial, and the probability of success is 0.7, then the probability of 0 successes is 0.3, and the probability of 1 success is 0.7. So we have 2 bars representing those 2 probabilities. If we make the sample size 2, we could have 0 successes, 1 success, or 2 successes with these probabilities. Now, these histogram bars right now do not look very normal. Here's the normal curve being graphed with the red line. But if the sample size increases, and it doesn't really have to increase to 30 necessarily, as the sample size increases, the distribution of the probability of binomial outcomes starts looking more normal. And we can really jack the sample size up, and those histogram bars start looking more and more normal. So, you know, how normal is normal enough, and is a often asked question, and that kind of depends, that kind of differs from one book to another. It's usually a combination of N and P that are discussed. Because for certain values of P, the sample size does not have to be very big for the distribution of binomial successes to look approximately normal. So anyways, back to this document. The usual rule of thumb is that the number of successes and the number of failures should both be at least 10. And in terms of proportions, that means the sample size times the probability of success should be at least 10, and the sample size times the probability of failure should be at least 10. So, putting that all together, we have a formula for the mean of the p-hats, a formula for the standard deviation of the p-hats, and a condition under which the distribution of p-hats looks approximately normal. Oh, and then we have to look at how our z-score formula gets modified, since we're often going to be changing a p-hat into a z-score. We subtract the mean of the p-hats and we divide by the standard deviation of the p-hats. So p-hat minus the mean of the p-hats over this radical, which is the standard deviation of the p-hats. So let's take a look at an example of all that. Suppose that the proportion of all Cal Poly Pomona students who live on campus is 15%. Because it said the word all, that's a population proportion. If we select a random sample of 200 Cal Poly Pomona students, what is the probability that the proportion of our sample that lives on campus is less than 13%? So the proportion of all Cal Poly Pomona students is telling us that P is 0.15. So even though in the word problem it's stated as 15%, we're almost always going to express that as a decimal. We have a random sample of 200 students, and the question is, what is the probability that the proportion of our sample, so that's P hat, is less than 13%? So we have this statement here. Checking the three conditions that need to be met. We were told that we have a random sample, so that formula is legit. Our sample of 200 is way less than 1/10 of the population of Cal Poly Pomona students. Therefore, this formula is legit. And the quote-unquote large counts condition is satisfied because n times P is 200 times 0.15, which is 30, which is greater than 10. And likewise with n times 1 minus P, that's greater than 10. So the distribution of P hats is approximately normal. So we take our P hat and we turn it into a z-score by subtracting the population P and by dividing by that radical, and we get a z-score of negative 0.79. So then once we have the z-score of negative 0.79, the probability of a z-score less than negative 0.79, we go over to our z-score table. There's z of negative 0.79, and we see right here 0.2148. So the probability of us getting a p hat less than 13% is 2148. The second question we had was, what's the probability that the proportion of students living on campus is between 18% and 20%? So we got to turn the 18% into a z-score by subtracting the population P and dividing by this radical, and change the 20% into a z-score by subtracting the population P and dividing by this radical. So the probability of a p hat being between 18% and 20% is the same as a z-score being between 1.19 and 1.98. Those two z-scores there. And we look at both of those z-scores on the table, and we subtract the numbers we get from the table, and we get this answer here.